In this video, we are talking about angular motion. We're kind of going back to the beginning, looking at objects that have a displacement, looking at velocity, looking at acceleration, but now how it pertains to things that are rotating. In fact, this is sometimes referred to as rotational motion. Okay, I kind of use these two words interchangeably, angular motion, rotational motion. All right, but it's really getting back to our roots. How do we just describe the motion of things that are moving in a rotational or moving in an angular way? Now, to start off, I really have a problem, which is how do we describe the motion of things that are rotating? Because up till now, we've always used translation, some change in position, physical location from one spot to another. Okay, we did that when we were looking at things moving in straight lines. Even in circular motion, we were looking at an object moving around, translating around a circle. And there's an inherent problem, or at least a complication with doing that for rotating objects. And to show that, I have my trusty old Phet. And here's a Phet simulator that has a wheel that's going to rotate. And we have two bugs. We have a ladybug right here and it looks like a beetle right here. And when I hit play, okay, it's not surprising. Obviously, they're moving around in a circle. You can see these little red acceleration vectors. That's representing those centripetal accelerations. And look at the velocity vectors. Well, the beetle has a larger velocity when we're thinking of our classic tangential velocity than the ladybug. And that should hopefully make sense because the beetle is traveling a larger distance. They're traveling a greater circumference. Now, of course, they're traveling one revolution in the same amount of time, right? If I was watching right here, both of them hit this starting point, and then it takes them the same time there. So if the beetle is traveling a further distance than the ladybug in the same time, it must have a larger velocity. But here's my issue. We don't really care about the ladybug and the beetle anymore. Now our focus in this unit is actually the spinning wheel. And so maybe you can sense my problem. If our discussion is now this spinning wheel, us using the classic way of describing motion, circumference over time, really doesn't work. Because where you are located on this wheel, you're going to have a different velocity. An atom right here that's obviously spinning or rotating around would have a smaller velocity than an atom, still part of the wheel, way out here. So that seems like it would make our analysis very confusing because we just have to know one more thing when we were discussing the wheel's motion. We'd have to know like how far away we were talking about. So instead, we need to think of a new way to discuss things that are moving. And that's really what this video is getting at. What's a different way to talk about how an object is rotating besides our classic translational method? I shouldn't have closed it. If instead, we focus not on the distance over time, but if we focused on the angle. So if we start our ladybug and our beetle right here, I'm not going to care about their distance, some number of meters, even if it's in a circle. I'm going to look at the angle. Think of this line. Here's our starting line. One moment later, there's a small angle, right? If we imagine this horizontal line, what was horizontal, now moving, it created a little angle. And as I keep progressing, that angle is increasing. We started right here, and now we're increasing in angle. But notice the ladybug and the beetle, because they're both on that line, they are both increasing the angle at the same rate. And that's what we're going to focus on now. That's, of course, why it's called angular motion. We're going to look at the angle that this rotating thing is covering, that it's subtending as it's moving, instead of those distances. So let me get back over here. This is what we're going to focus on. And I like to use the example of like a bicycle wheel because the spokes of a bicycle wheel give a nice visual. Okay. Instead, we're not going to look at just the path that like a little atom here is taking as it traverses. We're going to look at the angle that one of the spokes moves through. Okay. We need a reference line, just like we always need like a starting position. And we would usually say like, oh yeah, the starting position is 0 when we were talking about translational motion. We need the same kind of thing for angular motion. Let's just say the x-axis, because that's pretty convenient. Let's say that's always going to be our starting position. And let's just say that that's 0. It doesn't have to be, but that makes it easy. We could have always said that our starting position was 100 meters, but that's just one more number we'd have to worry about. So by convention, right here is our starting position. And as this wheel rotates around and around, if we watched one of those spokes, if we highlighted one of those spokes, if we put like a piece of tape on it, we could see what angle it creates. And that angle is going to be what we can measure our new kind of displacement. Not a change in meters, but a change in angle. So our starting angle is the x-axis, maybe some fraction of a second or a fraction of a minute, whatever later. Now it's right here. Here is our final angle, right here, final angle. And so what's delta theta? Well, it's just like our displacement. It's an angular displacement. It's theta minus theta naught. So this is really all we're doing. These are all cousins to our translational motion, just looking now at the angle. Okay, so let's start with angular position. And this is going to get faster and faster as we go. The angular position is given the symbol theta, Greek letter theta. And it's the angle between a reference line, again, which is often this x-axis right here, and a line, this is our technical definition, a line drawn from that axis to the location of the object. The object is just like some point that's on the rotating object. It could be like the edge of the wheel. But if the wheel started just at rest, and some moment later, if we just pick some random spot, the next spot, the line would go like this. So I can't draw. And this right here is our change in angle. This was our starting angle. This was our final angle. So maybe it had a starting angle if we were using degrees as 0, and then it ended up at like, I don't know, what does that look like? 70 degrees. All right, and then delta theta is just that difference. So angular displacement is the change in angular position. Okay, just like our old displacement was the change in position. Now, we're not going to use degrees. A lot of the equations we see are actually derived and defined using radians. Okay, you may be familiar with a radian. If you're not, radian is an angle, and it's the angle that you get when the amount of distance an object travels. So again, if we imagine this little point right here, if we're spinning this wheel until it gets to right here, okay, 1 radian is when this distance, this is known as the arc length. Okay, it's the arc that the particle is traveling as the wheel rotates. When this arc length is equal to the radius. So this radius right here, or if I picked a spot right here, this arc length equal to the overall radius of the wheel. So this is the definition of a radian. Now, I know what you're maybe thinking. Do I have to change my calculator into radians? And the answer is no. We're not actually going to be doing any trigonometry with radians. Okay, we'll be doing some basic math, like maybe you would find the arc length and you would divide it by r and you would get an answer in radians, 5 radians, 2.3 radians. But we're not doing any trigonometry. So no need, don't worry about changing your calculator into degree mode, because we have been using degrees for all of our other previous videos. So here's just the definition for a radian. Now, if we need it, 1 revolution, when this wheel rotates all the way around once, from here all the way around. Of course, that's 360 degrees. Hopefully you know that. But that's also 2 pi radians. We're not going to derive it. You don't really need to know where it comes from, okay, if you're not familiar with this. But that's what 1 revolution is. So if it says that a wheel or a door makes 1 complete revolution about its axes, when we're using these equations that we're seeing in this video, that's equal to 2 pi radians. Half of a revolution, 180 degrees, that's pi radians. 90 degrees is pi over 2, etc. Okay, but 1 revolution is 2 pi radians. Okay, so that was angular displacement. Everything else hopefully is pretty straightforward. We're dealing with cousins. Average angular velocity. All right, this is the cousin to our old linear or tangential velocity. This right here is lowercase Greek letter omega. Don't say W, that would seem silly. Okay, lowercase Greek letter omega. This is, of course, uppercase Greek letter omega, which more people are familiar with. This is just the lowercase version. So omega, the average angular velocity, it's the rate of change of angular displacement. Just like our old average velocity was delta x over t, angular velocity is delta theta over t. What would the units be? Radians over seconds. So again, maybe you're told that a wheel makes 1 revolution. So I'd plug in 2 pi, and it does that in 3 seconds. Okay, you could plug that into your calculator, you get some decimal that's in radians per second. That's average angular velocity. Not too bad. How about angular acceleration? Of course, I could get my wheel, and if I have it playing, here it has a constant angular velocity, But if I slide this dial up, we could watch the wheel speed up. Let's see, I'm going to slide it, going faster and faster and faster and faster. During that time I was sliding it, it was increasing in angular velocity. That's an angular acceleration. So average angular acceleration, this is lowercase Greek letter alpha. Greek letters are used for a lot of rotational symbols. It's the rate of change in angular velocity. So it's just delta omega over t. What are the units? Radians per second, or radians per second squared, often just rads per second squared. Okay, again, not really using trig, so no need to change the settings on your calculator. Here's a nice little table kind of showing our cousins. Okay, our linear, our old average velocity to our new angular average velocity. Old version of linear or tangential acceleration to angular acceleration. They look very similar. They're defined now in angle form, of course, but in very similar ways. Okay, there is a relationship between these two things. How do we go, or how do we get from a linear velocity to an angular velocity? It's a pretty quick derivation. Not that you'd have to do this on the AP test, but I think you all understand this enough for me to show you quickly. Our old version of velocity, it would be distance over time. And if we're talking about something that's moving around a wheel, we might use a very, very tiny like delta x, but really it's traveling along this arc length, this s. So the distance is really delta s, right? That's the path it's traveling. If it was one entire revolution, that delta s, of course, would be the circumference of the circle divided by t. So it's arc length divided by time. Oh, but wait a minute. From a little earlier on, we defined theta as being s over t. 1 radian, 1 degree radians, is 1 arc length over t. I'm sorry, not over t. S divided by r, excuse me. Well, that means that delta theta is delta s over r, because r would be constant. So delta s is equal to r times delta theta. Let me plug this right here, so that I go back to my orange. V tangential is equal to r times delta theta divided by t. What's delta theta over t? That's omega. So V tangential is omega times r. So here's our relationship between linear velocity and angular velocity. All you do is multiply the angular velocity times r. And again, this matches our ladybug simulator, because they would both those ladybugs would have the same angular velocity, but the ladybug that was farther away, a larger radius, must have had a larger linear or tangential velocity. You could do the very similar derivation for tangential, our old linear acceleration, and you would get this, the angular acceleration times r. This is not on the AP equation sheet, and I don't think you'd have to do math on the AP exam, but we'll do a little practice with this. It's very easy to go from one version to the other. Okay, the very last thing on my video, you should write it down, because again, we'll do a little math practice, but after we learned about the basics of motion, we looked at motion for things that had constant acceleration. Remember these equations right here? You have these same equations, the same cousins, for an object that's rotating with a constant rotational acceleration. So both of these are for constant acceleration, okay, for things that are moving in a linear type way and accelerating on the left, and things that are rotating with a rotational acceleration. But notice, where we had our old linear displacement, now we just have angular displacement. It's very similar. So we will use these equations a little bit, though they don't show up really too much on the AP Physics 1 equation sheet. Okay, so there is our introduction on the basics on how we approach the motion, the speed, the displacement, the acceleration of rotating objects. Thanks for listening.